So we just finished chapter 3 learning about limits. The first thing we're going to do in chapter 4 is we're going to use limits to come up with the definition of the derivative, which is our next major topic for this class. So in order to do this, we need to understand the difference between a tangent line and a secant line. You can see it in the picture. A tangent line is a line that just like barely brushes up against the outside of a graph and only touches it at one point. A secant line actually crosses right over a graph, and it ends up crossing it twice. And we're going to use both of these concepts for the definition of the derivative. But before we do that, let me talk about what the derivative is and why we want to learn it. So our first main goal of calculus is going to be to find the slope of the tangent line. So remember that picture I just showed you. You got this line that just barely brushes up against a graph. We want to be able to find the slope of that line. Now I'm gonna kind of hold off on the y for now. I want to make sure we know how to do it, and then later in the year I'll explain why the slope of that line is so important. Basically, the derivative, which is our next major topic for this class, is a formula that will give you the slope of the tangent for any line. All you have to do is plug in x. So let me go over a few notations we're going to use, and then we'll get back to that limit definition of the derivative. Okay, so the derivative, if we have our function, we'll call it f of x. The easiest notation is to put an apostrophe after the f. So when you look at it, it looks like f apostrophe of x. Now the way you actually say that in words is you say prime. So usually in a math class, if you see an apostrophe, you say the word prime. So I'm going to be calling the derivative f prime or f prime of x a lot. That's very common. And the name of the function can be different. The derivative of g of x is g prime of x. The derivative of h of x is h prime, etc., etc. Now let's say our function is just called y instead of f of x. Y equals this. The easiest notation is just use prime again. So y prime is the derivative of y. And then there's the secondary notation. I'm going to introduce it to you now because we might see it. It really becomes more important a little later in the year. This notation right here looks like a fraction. It has the letters dy on top and dx on the bottom. That also means the derivative of y. When we see something like that, what we usually do is just say the four letters in a row, dy dx. You don't need to say over or anything like that. You don't say dy over dx, just say dy dx. So dy dx is also the derivative of y. It's going to become more important later when we get to a little bit more complicated types of derivatives. For now, I just want you to know that any of those three things mean the derivative. F prime of x, y prime, or dy dx. Okay, so let's get back to the derivative. And basically, you guys did an activity in class yesterday which really got you started on this. I'm going to help you find a formula for the derivative, and it's going to have a lot to do with that activity. So I'm going to pause in just a second and bring up the activity, and we'll go over it together. But let's start with this. Let's say what I had you guys look at in the activity, we started with the graph of square root of x, and I'll start with the same one right now. So let's say this is my graph of square root of x, and I picked a point. I think I picked the point 1, 1. We'll put it right here. And then I drew the tangent line. So there's my point. If I draw the tangent line, you guys have to imagine a line that's just barely outside, like on top of the graph, that just barely brushes against it at that point and never crosses it again. So the tangent line looks something like that red one. So let's say I want to find the slope of that tangent line. Well, what I know, and I said in the activity yesterday, I said from earlier classes, you guys know we have slope formula. The slope formula tells you that m is y2 minus y1 over x2 minus x1. Now, we have one point. The problem is you need 2 points to use this formula. You need an x1, y1, and an x2, y2. Now, I have 1 point, this one right here, And let's call that the point xy. You can always call a point xy. That's like a generic one. Well, if I want to find a second point, this is how I'm going to do it. Let's say this right here is x. Now that's how a point works. The x part tells you how far to the right you go. Now instead of picking a second x value somewhere, I'm going to pick a value by adding to that. I'm going to say if this is x, I'm going to go a certain distance to the right of that, and I'm going to put my next point right here. Now what I'm going to do, I'm going to call that distance h, and you'll see why in just a sec. But once I get to that point on the x-axis, I'm going to go back up here and I'm going to pick another point. Now that point would be, so if you think about, let's do the x part first. Right here, this distance here is x. Because I called the first point xy, so I'm going over x. So basically, I'm going over to x, and then over h more. The first part of this point right here is x plus h. Now the second part of the point, and I'm going to go back and do the same thing to my first point. Instead of xy, I want to use function notation. So let's actually make that change right now. A different way to call this point, instead of x comma y could also be referred to as f of x. So let's do that instead. Now for my second point, match it to the first one. If your x value is x, you plug it into the function to find y. So if x is x, y is f of x. For my second point, this is where it can get a little confusing. If the first value is x plus h, then the y value is f of x plus h. So the first point is x comma f of x. The second point is x plus h comma f of x plus h. All right, now what I can do is I can go back and I can use slope formula to find the slope of that line. So let's make this one the x1, y1, and this one the x2, y2. So if I do on top, y2 is f of x plus h minus y1, f of x, over x2, which is x plus h, minus x1, which is just x. Now the only thing that cleans up a little bit in there is in the denominator. I have a positive x and a negative x that will cancel. So the slope is f of x plus h minus f of x all over just h. Now the problem is that's not the answer to my question, because what I actually found was not the slope of that red line, it's the slope of the line, I'll draw it in blue here, that goes through those 2 points. So you can see just by looking at the picture, it's not the right answer. Those 2 lines have different slopes. The slope of the blue line is a little bit less than the slope of the red line. Now this is where your activity comes into effect from yesterday. So what I'm going to do, I'm going to pause the video here. I'm going to go back to Desmos, open up your activity from yesterday, and show you what the point of that was and how it's going to affect us here. All right, so here's our activity from yesterday that you guys did. It actually looks exactly like the picture I drew from the notes. I made it match so it would be perfect. The dotted red line you see is the tangent line we're trying to find the slope of. The orange line is the secant line that we actually found using 2 points. And you can see, again, just like in our notes, they're not the same. So here's what I had you guys do. I had you guys kind of drag that point around a little bit and see what happens. And the whole goal of this activity was for you guys to see, if I grab this orange point and drag it, the closer I get to the red point, the closer I get to the right answer. If I go about halfway there, those lines, see, I started here. Those lines are pretty far apart. If I go about halfway back, those lines are getting closer. If I go half of that distance, they're getting closer. The closer I put the 2 points together, the closer the 2 lines are. If I get right here, those are almost the same line. If I get right on top of each other, you can see they pretty much are the same line. Now, if I go right on top of that point, if I make them the same point, then we can't make a line, because that was the whole point. We need to use two separate points to use the slope formula. So the idea is we want it like this. We want these points to be as close to each other as they possibly can be without quite being the same point, and then our secant line turns into our tangent line, and we found the slope. Now, if that concept seems familiar to you guys, that's a limit. That's what we just finished talking about for chapter 3. If we want two things to be as close together as possible without quite being the same thing, that's a limit. So let's go back to our notes and see if we can figure out how the limit would apply to the work we just did. All right, so here's where we left off in the notes. What we decided is that if we take those two yellow points and get them so close together that they are almost the same point but not quite the exact same point, the blue line basically turns into the red line and we have our tangent line. So what we really want is, and this is why we set it up this way, instead of picking a second point as just any point, we set it up as a distance away from x. See, now what we want is for that distance to be as small as possible. The way we say that with limits is we want h to approach 0. Meaning we want the distance between them to be as close to nothing as possible without quite being nothing. If h was actually 0, then the 2 points become only 1 point and you can't use slope formula. So they have to be two separate points, but we want them as close together as possible. So we want h to approach 0. So basically, if I take my slope over here and I squeeze in front of it the limit as h approaches 0, then the blue line turns into the red line, and we found what we were looking for the whole time, the slope of the red line. So basically, that's going to give us what we call the definition of the derivative, which is a formula. And it looks like this. F prime of x, that's our notation, that means the derivative of f of x, is the limit as h approaches 0, remember h was the distance between the 2 points, of f of x plus h minus f of x all over h, which was the slope of the blue line. So we basically turned the blue line into the red line and found its slope. So this formula right here, it's one you want to know. This formula will create an equation that will give you the slope of the tangent of any line of f of x by just plugging in a number. So when it comes to using it, the first step to using it is this thing right here. So remember in chapter 1 when we went over function notation, finding f of x plus h means taking your function f of x and substituting x plus h for x. And that's one of the places this question can get a little tricky, is you have two different variables. You have both an x and an h in the problem. People get confused by that, but once you get used to it, it's really not that bad. So let's do our first derivative question. So I said we have a function, f of x equals 3x squared minus 2x. Let's find f prime of x. Well, I'm going to do this in parts. Because I know I'm going to need it in the definition of the derivative, the first thing I'm going to do is find f of x plus h, which means I am going to substitute x plus h here and here into my original equation. So what I will have is 3 times x plus h squared minus 2 times x plus h. And when you go to clean that up a little bit, now remember this is a common mistake. You can't distribute the exponent here. X plus h in parentheses squared doesn't just equal x squared plus h squared. A lot of people do that and that's the mistake. X plus h squared, what it means, and I'll switch colors so it stands out. It means x plus h times x plus h. And then you have to multiply it out. You FOIL it out. You get x squared plus xh plus another xh plus h squared. And then you can combine those two terms in the middle. You get x squared plus 2xh plus h squared. So that is what's going to go right here. X squared plus 2xh plus h squared. And I'll leave the next one for now. We're going to distribute the 2 anyways, but we'll just distribute the 3 and the 2 at the same time. So if I distribute the 3, I get 3x squared plus 6xh plus 3h squared. And then if I distribute the negative 2, I get negative 2x minus 2h. So I'm going to remember all of this. All of that was kind of the first step that I'm going to use. I did that work separately because I wanted to have it done. So let's go and finish the question. I'm going to go to a new screen because I ran out of space. So basically what I have so far, this was the original question from the problem. What I just found from my work was that f of x plus h equals 3x squared plus 6xh plus 3h squared minus 2x minus 2h. I'll write that down so we have it for later. Now for the work, I'm going to use the definition of the derivative. The definition of the derivative says f prime, this is the one we just created, it's called deriving. We derived this. It's the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, before I even start this question, before I plug anything in, notice, if you do direct substitution right now, you're plugging in 0 for h, and you have h in the denominator. So this is going to be undefined no matter what. This is going to turn into one of those, it actually turns into a 0 over 0 question every time. So let's go ahead and try this out. Let's substitute what we just had. Now I'm going to stretch this all the way across the board. It gets a little bit messy. F of x plus h is what we have written in yellow up there. That's 3x squared plus 6xh plus 3h squared minus 2x minus 2h. And I'm going to subtract from that f of x, which is the original question. That's 3x squared minus 2x. And the whole thing is over h. Now what happens is everything in this question, everything from the second term, everything from f of x cancels. Like right here, I have a 3x squared minus a 3x squared. That cancels. And right here, negative 2x minus negative 2x. That cancels because minus a negative turns into a plus. So it does clean up a little bit. We end up with 6xh plus 3h squared minus 2h, and it's all over h. Now remember, I told you guys, if you try direct substitution, you're going to get 0 over 0 here, because that's how definition of the derivative works. Your goal is always the same thing. I got to find a way to cancel out that h in the denominator, because that's causing the 0 over 0. Now what you notice, if you look on top, now that we canceled out the f of x terms, there's an h in every term. You can factor that out. So if I factor out h on top, it would leave 6x plus 3h. Remember, there was an h squared there. I took one h out. There's still one there. And then minus 2. And the whole thing is over h. And now I can do this. I canceled out those h's, which is what I wanted to do the whole time. So what's left over now is the limit as h approaches 0 of 6x plus 3h minus 2. Now what you want to do is direct substitution. So you're still plugging in a 0 for any h's that are left after you canceled out that 1. And I have one right here. Now when you plug in a 0 for something, it basically just disappears. 3 times 0 is 0. So my final answer to this question, if I plug in a 0 for that h, my final answer to this question for f prime of x is what's left over. That's 6x minus 2. Now remember, I told you the derivative doesn't give you an answer. Your answer isn't going to be 20 or negative 3. It can be, but it's not very often. The derivative gives you a formula that you use to find the slope of the tangent. And this is my formula right here, 6x minus 2. So these are long problems. I will tell you in advance the good news. After we do this, for the rest of the year, it's all about finding shortcuts. It's all about finding better, quicker ways to do derivatives, and there are, trust me, much better, quicker ways. But we want to learn this way first because this gives you your foundation, this gives you your basis, and make sure that you really understand how to do the definition of the derivative. All right, I want to do one last example with you guys. I know this is definitely our longest day of notes for the year. But let's do this. So this time our function is f of x equals square root of x, the same one you guys looked at the activity and the same ones I used earlier in the notes. So let's find the slope of the line tangent where x equals 4. So we're going to find the derivative, but instead of just finding the derivative and having a formula, we're going to go one step further and use it. So let's do this. I'm going to say this. F of x plus h in this case, if I substitute x plus h right here, there's no extra work. That's why I didn't even bother doing it off to the side or anything. It's just the square root of x plus h. So if I jump straight to the derivative part, let's set up our derivative again. So f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. And that part, what I just wrote, that part will never change. That part doesn't change. That is the definition of the derivative, and it works for any function f of x. So what I'm going to do is I'm going to put the two things in. F of x plus h is the square root of x plus h. F of x is the square root of x, and it's all over h. So what we have to do is, same as last time, I need to find a way to cancel out that h in the denominator. Now, if you remember when we did limits analytically, I focused on 3 problems. One of them was factoring, which we just did in the last example. One of them is complex fractions, which you'll see in the homework. One of them is this one, and that's rationalizing when you see square roots. So I said back then, one of the tricks you guys can use here when you have square roots is you can try multiplying by the conjugate. And conjugate means the same thing but with a plus in the middle. So instead of the square root of x plus h minus the square root of x, I change that to a plus. Now it is a fraction, so you always have to multiply top and bottom by the same thing. And when you multiply the conjugates on top, remember, basically we have a little shortcut. It just ends up being the first thing squared minus the second thing squared. So this one squared, when you square a square root, it cancels. So we'll just have x plus h. Minus this one squared, same thing. Square square root, those cancel, and it just leaves x. Now it's all over, don't forget this part. That's a common mistake. Sometimes people just put it over h and stop. It's over h times the square root of x plus h plus the square root of x. Okay, now what we do, on top you have a plus x and a minus x that will cancel. And I'm going to switch to a blank screen again. So right now, here's our original problem. Right now, we have the limit as h approaches 0 of h over h times the square root of x plus h plus the square root of x. Now remember, our goal the whole time for this question is to cancel that h. We can do it now. That h here will cancel with that h there. It does leave a 1 on top. So what I have is the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. And now we can do direct substitution. Now I can plug a 0 in right there for that last h. So what I get, when I plug in 0, remember the h's basically disappear. So you get 1 over square root of x plus square root of x, or basically 1 over 2 times the square root of x. Now that's our derivative. That's f prime of x. If this was like the first example, we would be done. We would say, I found my derivative, I'm done. But what I actually asked you in this question is, find the derivative, find the slope of the tangent when x equals 4. Because I wanted to show you what the derivative is actually used for. So what I'm actually asking you, we're pretty much done with the question. The rest of it's super easy. You've done the hard part. What I'm saying now is take that formula you just found for the derivative and plug 4 in. Plug 4 in for x. Basically, find f prime of 4. Well, that would be 1 over 2 times the square root of 4. Now the square root of 4 is 2, and 2 times 2 is 4. So the final answer to the question is 1/4. The slope of the tangent at that exact point where x equals 4 would be 1/4. The extra work, the difference between our first example and this one, is just that tiny bit of work I did in red there at the end. Once you have the equation for the derivative, I can find any tangent line by just plugging in an x value. So if I said, what's the slope of the tangent when x equals 10? Just plug in 10. If I say, what's the slope of the tangent when x equals 1 million? Plug in 1 million. It doesn't matter. You can plug in any number you want, and that equation will automatically give you the slope of that tangent line. And remember, I said, for now, I just want to focus on how to do it. As the year goes on, I'll explain to you why that slope of that tangent line actually is very important.